Hello everyone, this is a video about Rolle's theorem, mean value theorem, and four theorems that we need to know for the course. So the first theorem is Rolle's theorem, and Rolle's theorem tells us that if a function is continuous and it is defined on a closed interval, right? So we want brackets here. The function is continuous on a closed interval, and it's also differentiable. That means smooth, and you can find a derivative on the open interval AB. Then if the y values at the two ends, f of a is equal to f of b, if that happens, there must be some place in the interval where f prime, or the derivative, or the slope of the tangent line is equal to 0, right? Some point in the interval AB. So looking at this from a graph standpoint, it means this. If you have an interval from A to B, and if you have a function here that is continuous on the closed interval, that means you need filled in circles basically at the ends. And you have whatever the function is, if it is continuous, and you notice that the way I drew it, I also drew it smoothly. That means it's differentiable. It's differentiable on the open interval. That means all the way from one end of the interval to the other. Then notice also that I drew it this way, where the function y value at one end is equal to the function y value at the other end, right? So here the point is a f of a, and here the point is b f of b, but f of a and f of b are the same y value, right? So if all of this happens, if these three conditions are met, then for sure there's at least one place along the way where we have a horizontal tangent line, right? That's what the theorem says. This is one place. The way I drew this, there's a few other places where there is a horizontal tangent line. The theorem says that there will be at least one place, right? But there might be more. Let's do example one. Example one says let f of x equal x cubed plus 3x squared minus x minus 4 on the interval negative 3 to 1. And notice that we are on a closed interval here. Find all the numbers c that satisfy the conclusion of Rolle's theorem. So we're looking for x values, x equals c, where we have a horizontal tangent line, right? That's what Rolle's theorem helps us to find. Okay, so let's first of all see if we meet all the conditions. So we would say f of x is continuous. It's a polynomial. It's continuous everywhere. We need it to be continuous on this closed interval, and it is. Secondly, f prime of x is equal to 3x squared plus 6x minus 1. So that's a parabola, and that's also a polynomial. And therefore, f of x is differentiable, right? If f prime exists, which it does everywhere, then f of x is differentiable, and we need it only to be differentiable on negative 3 to 1, the open interval. So we meet the second condition. The third condition is that the y values at the two ends of the interval have to be equal to each other. So we put this is our a and b from the theorem. That's our interval endpoints. So at the endpoints, f of negative 3, go back to the f equation. F of negative 3 is equal to negative 3 cubed plus 3 times negative 3 squared minus negative 3 minus 4. And this comes out to be 3 minus 4. The first two are both 27 and negative 27. Those cancel. And so f of 3, negative 3 is negative 1. F of 1 is 1 plus 3 minus 1 minus 4, which also comes out to negative 1. So the y values at the two endpoints are equal, and that's this third condition of Rolle's theorem. So the three conditions are met, so we can now find where the horizontal tangent line is. There will be at least one place on this interval. So we take our f prime equation, 3x squared plus 6x minus 1, and set it equal to 0. Now at this point, depending on the f that you started with, you'll have all different types of things you have to do to solve the equation. In this case, it's a quadratic equation, and it's not factorable. So we will resort to the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we do this carefully, negative 6 plus or minus the square root of 36 plus 12 makes 48 over 6. And simplifying this down, we're going to get that the two roots are at negative 1 plus or minus 2 rad 3 over, oops, sorry, messed up there. Went a little too fast. Let me do it again. Negative 1 plus or minus 2 rad 3 over 3. This will be our two places. Okay, so then we go in our calculator and we find decimal values for these. And these two values will be negative 2.155 and 0.155, right? So we are looking for the places on this interval where we have a horizontal tangent line, and we've actually found two places because both of these are within the interval from negative 3 to positive 1. So if you actually were to plot this, function, which you don't have to do to solve the problem, you would find that it looks something like this. We start at negative 3 and y is equal to negative 1. Then the function goes up and down, and then we have a y-intercept here at negative 4, and then it comes back to at x equals 1, y is again negative 1, right? So this is the start of the interval, this is the end of the interval, the y values at the two ends are the same, and the horizontal tangent lines that we found are right here at x equals negative 2.155, that would be that one, and another horizontal tangent line, it's right around there, which is x equals 0.155. Okay, let's take a look at the next example. Verify that the function f of x equals cosine of 2x satisfies the three hypotheses for Rolle's theorem on the interval from negative 3 pi over 4 to 3 pi over 4, and find all the numbers c that satisfy the conclusion of Rolle's theorem. So the hypotheses are that f of x has to be continuous. So this is a trig function, just a plain cosine function, right? Not all trig functions are continuous. Tangent in particular has all those vertical asymptotes, right? Or even secant and cosecant, but this one is continuous, and cosine is continuous everywhere. So we can say that it's continuous on negative 3 pi over 4 to 3 pi over 4. The second condition really is right here, that it's a closed interval, right? So we can repeat that and say we are on a closed interval of negative 3 pi over 4 to 3 pi over 4. And then the last condition for Rolle's theorem is that f of 3 pi over 4 has to be equal to f of negative 3 pi over 4. So at the two ends of the interval, we have to have the same y value. So putting 3 pi over 4 into the function, cosine of 3 pi over 2 is equal to 0. Cosine of negative 3 pi over 2 is also equal to 0. So these are the same, and we have now satisfied all three conditions of Rolle's theorem. So that is the first part of the question. Hypotheses mean the conditions, right? The three hypotheses are the three conditions. And now we are going to find the number c that satisfy the conclusion. So for that, we take the derivative. So the derivative here is f prime of x is equal to negative 2 sine of 2x. And that's what I need to check, whether there are any DNEs. So always thinking, is there any place where f prime equals DNE? This sine function is just a continuous function, no breaks, no holes, no asymptotes. So there's none of that. And I just have to do f prime equals 0 and find those x values. So negative 2 sine 2x equals 0. So we solve that equation, and to solve it, divide both sides by negative 2. So sine 2x equals 0. That means that 2x is one of these values on the start of the unit circle, right? Sine function is going to be 0 here and here and here and here, right? So every time 2x is equal to 0 or pi or 2 pi or negative pi, negative 2 pi, etc., right? Those will be the places where this equation is satisfied. So x is equal to 0, comma pi over 2, comma negative pi over 2, comma pi, comma negative pi, right, etc. Now, we only have to worry about those values that are within this interval, negative 3 pi over 4 to 3 pi over 4. So that would be just this, and this. Those are my three C values. Those are the numbers C that satisfy the Rolle's theorem. That's the conclusion of the Rolle's theorem. So, right, so that C is equal to negative pi over 2, 0, and pi over 2. F of x, right, will have a horizontal tangent line. In other words, f prime of c at those points will be equal to 0. Okay, so graphically, again, we don't have to graph to solve the problem, but always good to understand it better. Cosine 2x, that was our function, and it was basically a cosine function oscillating twice as fast as a normal one. So that means I start, as usual, at 1, and then by the time I'm at pi over 4, I'm already at 0, and then at negative 1 at pi over 2, and then back up to 1 by the time I hit pi, right? So this is our function, looks something like that. On the other side, same thing is happening, and so the function looks something like this, okay? So that means that we have a horizontal tangent line. You can see that we're going in the problem only from negative 3 pi over 4 to 3 pi over 4, which means the interval that we're looking at is right here, this interval right here, right? And you can see that my horizontal tangent lines were at 0 and pi over 2 and negative pi over 2, right? That's what we found here as our answers. And graphically, that makes sense. That's where we would find our horizontal tangents for this particular function. Okay, moving on to example 3. Example 3 says a particle is moving in a horizontal line so that its position is given by a continuous differentiable function s of t. And then the question says, if the particle is in the same place at two different times, t equals a and t equals b, what conclusion can we draw about the velocity using Rolle's theorem, right? So position and velocity and acceleration functions are going to be continuous because they are physical quantities and cannot just change abruptly, right? So it's a given, and it actually was repeated to us here that the position is a continuous differentiable function. If the position is continuous and differentiable, then that means the velocity is at least continuous, right? So that can be inferred from the question. The next thing we are already satisfying some of the hypotheses, right, of Rolle's theorem. The next part of the question says the particle is in the same place at two different times, A and B, right? So that means we have some stretch of time where S of A is equal to S of B. And basically those are now the three conditions for Rolle's theorem, right? Because we have a continuous function, a differentiable function for S, and S of A equals S of B. So what we're really saying is that the particle is doing something continuous between A and B. Not only is it continuous, it's differentiable. It's smooth between A and B. And we started at some position, S of A, that's the y value there, and we are ending at that same position, S of B, right? So that means that the function had to turn, and it basically had to turn in a smooth way. And that's Rolle's theorem, right? So in other words, I made it turn twice. It could also have just done something like that, right? The position could have done that or that, right? But whichever way it did it, it had to turn at least once, and it had to turn in a smooth way, which means that it must have had a horizontal tangent line, right, at least once along that time, or rather along that time interval, right? The time interval is from A to B, and this position function must have at least one horizontal tangent line at some time C, right, within the time interval A to B. So there must be some S prime of C, which is equal to 0, which means that's saying that we have a horizontal tangent line, right? S prime is the slope of the tangent line, must be 0 at some spots, some time C, and that means the velocity must be 0 at some time C. So we could answer the question this way. It said, what conclusion can we draw about the velocity using Rolle's theorem? And we would have to say, let's say it carefully, we'd have to say, first of all, that S of t is continuous. So we're basically, every time you apply a theorem, you have to establish that you are justified in applying the theorem, right? So S of t is continuous on AB. S of t is differentiable on AB, and S of A is equal to S of B, right? All of this is really given in the question, but we have to say, since these things are true, then Rolle's theorem guarantees that there is at least one time t equals C on AB, on actually the open interval AB, when V of t is equal to V of C is equal to 0. So that means that in order to basically turn around, which it must have done to get back to the same position, the velocity had to become 0 at some point. Okay, so let's take a look now at the mean value theorem. Mean value theorem is a broader theorem. Rolle's theorem is actually a special case of the mean value theorem. Mean value theorem, or MVT, says that if f of x is continuous on a closed interval, AB, right, so same as Rolle's, and it's differentiable on the open interval AB, so again, same as Rolle's, then there is some point x equals c, some x value, x equals c, in this interval from A to B, where the derivative f prime of c is equal to the average rate of change on the interval, right? So in other words, let's take a graphical look at what this is saying. It's saying that if we're going from a x value A to an x value B, and now the y value is f of A when we're at A, and it's f of B when we're at B, right? So no longer are the two y values the same, they're different. But we're going from A to B in some kind of smooth and continuous way, right? It could be like that, or it could be like that. Whatever way it is smooth, it is continuous. In that case, there must be at least one place along the way where the tangent line, right, the tangent line slope is equal to the secant line slope, right? So the secant line here is the blue line between A and B, and the slope of that is this equation, f of B minus f of A over B minus A. We're saying that there must be some place where the slope of the tangent line is equal to the slope of the secant line. The slope of the tangent line is the derivative. It's changing all the time, right? We're saying there's at least one place, and that's right here, it looks like, right? In the picture that I drew, there's one place there where the slope of the tangent and the secant are the same, so they're parallel. And there's another place, it looks like, right around there, where also the slope of the secant and the tangent are the same, right? So in this black graph, there would be two places. If I were looking at the red graph, it looks like there would be only one place, right? So how many times this happens depends on the exact shape of the graph. But if we are differentiable on the open interval and continuous on the closed interval, this will happen at least once. Okay, so let's take example 4. It says let f of x equal x squared minus x, and I'm going to change this to a plus 1, x squared minus x plus 1, so it's a parabola on negative 1 to 4. And we are finding all the numbers C that satisfy the conclusion of the mean value theorem. So we start by checking if we satisfy the conditions or the hypotheses, right? So we're going to say, we can even say, since f of x is continuous, it's a polynomial, it's a quadratic, it's continuous on negative 1 to 4, and it's also differentiable, right? A polynomial will also be smooth and differentiable everywhere. We just need it to be that on open interval negative 1 to 4. Those are the two conditions of mean values. So since those are satisfied, there will be some f prime of c, where c is an x value, where f of 4 minus f of negative 1 divided by 4 minus negative 1, right? This is like my a, b in the theorem. It's the interval goes from negative 1 to 4. This equation right here gives me the secant line slope. And I'm saying that somewhere along the way, the tangent line slope, right, this is my tangent line or derivative, tangent line slope, will be equal to the secant line slope. So now we just take the derivative, which is 2x minus 1. I'm going to call it 2c minus 1 because I'm looking for this particular place c where this happens. So 2c minus 1 is equal to f of 4. You may want to go off to the side and figure out that f of 4 is equal to 13, and f of negative 1 is equal to 3. So we get f of 4 minus f of negative 1 over 4 minus negative 1 is 5. So 13 minus 3 is 10. 10 divided by 5 is 2. 2c minus 1 has to be 2. 2c equals 3. c equals 3 halves. So that means that at x equals 3 halves, my tangent line slope, which is my derivative value, will be equal to the secant line slope across negative 1 to 4, right? If you look at the graph of this function, actually it's pretty easy. You could even figure this out without a calculator probably, but x squared minus x plus 1 from negative 1 to 4. The graph is a parabola, right? And you can see that we figured out that at x equals negative 1, my y value is 3. And at x equals 4, my y value is way up here at 13, right? So the parabola looks, so this is 4, 13, and this is like negative 1, 3. And the parabola looks, something like this along the way. It has to go through 1 because that's the y-intercept, and then it does something like that, right? So there's the parabola, and we are just looking at it along this interval, this span right here. And what we're saying is that the slope of this line right here that connects the two ends of the interval is going to be equal to the slope of the tangent line at x equals 3 halves, right? That was the c that we found, right? So my picture is not perfect, but you can see that this blue line and this red line, right, look just about like they have the same slope. They're parallel. So that's what the mean value theorem predicts, that there will be at least one place like that, and we are able to find it. Okay, last problem is right here. Does f of x equals 1 over x satisfy the hypotheses of the mean value theorem on the closed interval 1, 3? If yes, what are all the numbers C that satisfy the conclusion, right? So let's think about 1 over x. If you are looking at 1 over x, it's that hyperbola, and f of 1 is 1 and f of 3 is 1/3, right? The whole graph looks something like that, right? But we're only looking at this little stretch of the graph in this part of the question. And so they're asking whether we satisfy the hypotheses. So I would say yes, we do, because f of x is continuous on 1, 3, It also looks pretty differentiable, right? It's differentiable, smooth on 1, 3, right? So we do satisfy the conditions, and if we were trying to find the place where the secant and tangent lines are parallel, then we'd have to do f prime of x or f prime of c, which is equal to -1 over c squared, right? That's just taking f of x, which is x to the -1, and differentiating it into -1 over x squared, right? So f prime of c has to be equal to the secant line slope, which is f of 3 minus f of 1 over 3 minus 1. F of 3 is 1/3, f of 1 is 1 over 3 minus 1 is equal to -1 over c squared. So that gives me -1 over c squared is equal to -2/3 over 2. The 2's cancel out, the negatives cancel out, so I'm looking at 1 over c squared is equal to 1/3, which means c squared is equal to 3, which means c is equal to plus or minus the square root of 3. I'm not going to be interested in the minus because I'm on the positive interval 1, 2, 3, right? So my c value that I want is c is equal to the square root of 3. Okay, so the square root of 3 turns out to be roughly 1.7320. Keep it to 4 decimal places. So what we're saying is that roughly, well, not roughly, but precisely at 1.73, if you draw the tangent line, that's going to be parallel to the secant line across that whole interval. Okay, so you can think about this question on your own. I encourage you to do that. Do we satisfy the hypotheses of the mean value theorem on this function 1 over x from -1 to 1? Okay, so I'll let you think about that. And I want to end. Okay, so I want to end this video with a quick recap of the 4 theorems that are in AP Calc AB, right? And these are intermediate value theorem IVT, extreme value theorem EVT, Rolle's theorem, and mean value theorem MVT. Since we just talked about Rolle's and MVT, let's quickly write those down again. Rolle's theorem says that you have to be continuous on the closed interval, differentiable on the open interval, and you have to have the 2 y values at the ends be the same. If that happens, there's definitely one horizontal tangent line somewhere in the interval, right? So graphically, we're looking at this. We're on an interval from A to B. The interval is closed, which means it got filled in circles at the 2 ends. It's smooth, the function, which means I have to be no abrupt like V shapes or cusps or anything like that. If that happens, and if these 2 y values, right, notice how I drew the function coming back to the same y value. It can do that in whatever way it wants to, but there will be then at least one place where there is a horizontal tangent line, right? And we called that place C. Okay, then mean value theorem says it's really Rolle's theorem on a slant. You know, if you think of the mean value theorem, it's saying the exact same thing as Rolle's, except the 2 endpoints don't have to be the same y values. So the function can be doing something like that, and we're saying you take the secant line, there's going to be at least one place where you're going to find a tangent line that's parallel. But when I say one place, I mean one or more x values, and we call those C. Okay, just recapping the extreme value theorem, that was also recently in lesson 5.1, and that one is saying when are we guaranteed to find an absolute max and an absolute min, capital M and little m, right, for maximum, absolute maximum, and absolute minimum. When can we guarantee that? Well, we can guarantee that if we're looking at a continuous function on a closed interval. It's as simple as that. If you have a closed interval and a continuous function, there has to be an absolute max or min, right? So closed interval, continuous function. It doesn't have to be differentiable. Any of those things I drew has an absolute max, one or more, and an absolute min. You know, as an aside, the problems with absolute max and min happen when we have things like this, going on, right? Like this, so that one won't have an absolute max, right? Or you might, if you have a break, like an asymptote, in the middle of your interval, say this is AB, then obviously we could have like no absolute max or min in a problem like that, right? So continuity is definitely going to be important on the interval. And the interval has to be closed, because if not, we talked about this in class, if we have something like that, then clearly at the two ends we don't have an absolute max there, right? So this is why for EVT we need continuous and closed, because EVT deals with absolute maxima and minima. Okay, the last one, which you might have forgotten, is the IVT, the intermediate value theorem. And this one is about, remember, the intermediate values, all the values that are in between f of A and f of B, right? So this is the one that says, if you start somewhere here and you end somewhere here, so this is my f of A, the y value, and this is my f of B, the y value that I end at, right? Then if the function is continuous, then every single y value in between will appear at least once in the, as I go from A to B. So, whatever line you draw basically from A here to B, let's call this guy here A f of A, right? That's the point here. A is the x value, f of A is the y value. This is B, A, so this is B, f of B. Whatever line you draw, if you don't pick up your pencil from the paper, right, whatever way you go from A to B, I'm trying to just draw all these different ways, whatever way you go, if you don't pick up your pencil from your paper, you have to cross every y value intermediate between f of B and f of A. We use the intermediate value theorem for things like in Unit 1 we said, here's a function, use the intermediate value theorem to show that we have a 0 or an x-intercept on a particular x interval, right? Use the IVT to show that. And the way we would show it is we would say, okay, so f of 1, you plug it into the equation, it comes out to be -1, which is less than 0. F of 2 at the other end of the interval is equal to 12, so that's greater than 0, right? So that's telling me that this function, which is continuous because it's a polynomial and I'm on this closed interval, I'm going basically from -1 when x is equal to 1 to +12 when x is equal to 2. I'm up here at 12. 2 comma 12 is on the graph. 1 comma -1 is on the graph, right? And if I know I'm continuous, then I must have crossed the x-axis at least once. So we can use the intermediate value theorem for problems like that, but remember that it's not just for crossing y equals 0, it's for crossing all the values, all the y values that are along the way from f of A to f of B. Okay, so that's basically our takeaways. Of course, Rolle's and mean value theorem are our two new theorems, but we also want to use the opportunity to remember all four, I call them the Fab Four, Calc AB theorems. I hope you're having an awesome Thanksgiving break. Thank you for being a diligent calculus student and putting in time to doing this lesson. Have a wonderful break with your families, and I will see you back on the 28th or 29th, as the case may be. Bye.